Alrighty, folks, it looks like we have all the boards up there. Just about all of them. There's one that, because of the ice storm, got stuck in first class. And they are just about done. They are just about done fixing it, so we will let them add it as they go. Did we get them organized based on school characteristics?
I emailed them to you as well.
Yes. Is that a yeah or an yeah? We have them organized?
Where are they? Yes.
So it looks like these two over there are not the same. These two look good, right?
Yeah, I'm sure it is.
And a 160 and a 200. Let's put this one by, here's another 160 and 200.
That's 120. There's 120. 160 and 120, the blue one.
Oh, okay.
Yeah, those two are organized. We had like an odd number of groups that were like 2 hours an hour.
That's right, I forgot about that. Let's put this one down here by these. There's another 160.
The last one is right there. 160 and 120, that's that one.
Oh, and this one goes down there also, right?
Yeah.
And this one's all by itself?
Yeah.
Okay.
What is that one? Like 160 and 120? Yeah. That one's 160 and 120.
All right, well, when you take a look at the overall relationship, you tell me, what is it? Linear. With an intercept or without an intercept? Okay, so we've got linear with no intercept. We like that because that's the easiest relationship. We can write that the electric potential difference is proportional to the current. Like we've been practicing, let's also put that into some conceptual terms. So what does that graph tell us about that relationship?
Proportional.
Well, even easier, besides it's proportional.
As the electrical,
that way.
as the voltage increases, the current will also increase.
Yeah, that seems pretty straightforward. As the voltage increases, so does the current. You said that there's no intercept. Why conceptually does it make sense that there would be no intercept? Okay, a little bit louder so for everybody. Calvin?
I said when you turned it off, there wasn't any current or potential.
Yeah, I mean, I think we all kind of have the same idea that if we've defined electric potential difference as the energy per charge, and it's that difference in electric potential that is what's causing the charges to move. Well, if I don't give the charges any energy, there's no difference, right? There's not going to be any movement of the charge. So conceptually, hopefully that all makes sense all the way through. We're okay with that? All right, let's take a look at, then, the slope. When we take a look at the slope itself, what's one of the things that we should notice? Positive slope, good. Well, we'll get to the units in a second. Let's just focus on the value. Or values. Mark?
There's lots of different slopes, so it's not universal.
Yeah, It's not a universal constant, because all of the values are a little bit different. So it's not a universal constant, but because it's a linear graph,
Constant for each group.
we know it is constant. Lexi, what did you say it was constant for?
Each group, I guess it would be a particular age and wire.
Yeah, let's just call it's constant for a particular school. And when we did the pre-lab discussion, you thought there were 3 factors about the school that might affect the relationship.
Gauge.
Okay. What did the gauge relate to again?
How thick
The
the wire was,
cross-sectional area.
Cross-sectional area, thickness.
higher gauge, the thinner wire.
And you said length? And what was the third one?
Material.
Material.
We didn't vary the material.
We did not vary the material, but we are gonna talk about it.
Okay.
All right, so let's look at the slope value and see if there are any relationships that pop out about those particular school characteristics. So focus your attention back to the boards. Wait, Calvin, what's one of them?
As the gauge increased, the slope decreased.
Calvin's group observed that as the gauge increased, the slope number went down. Is that confirmed by any other group? No?
No, ours is not, yeah, I don't know, since the opposite. I don't know.
Well, here's all the groups that did that. Let's go right back to the data.
We don't have any data like first one.
So this one we don't have an equation to line on?
No, it's lost the first one.
Oh, that's the first pass one. Okay, I'm sorry, yep. All right, so here we had the dotted line is the 30 gauge, and we know that the higher the gauge, the thinner the wire. So this would be a thin wire.
Oh, I have mine.
This would be a thicker wire.
Oh, you're fine.
So you want these two, you're gonna fix that?
Yeah, ours is actually the line.
Well, what about this group? Yeah, so they've got the bigger slope value written on the smaller one. Whose was this one? Yeah. Should those be switched also?
Our graph in green and the one next to it are the same,
So these 3 all agree.
or the red one.
Oh, that's the length.
Yeah,
These
ours
2
are-
agree?
Yeah, we have the same 2 schools and they're the same.
So we're just wondering about this one.
Yeah,
All right. Alright, so we'll make this one the 28 and this one the 14.
What is that?
Alright, so let's write that down. So the slope value is greater with thinner wire. Okay. How about with the length factor? That's the rest of the board. Do we see a pattern emerging from that one?
The one that's got in the black, the one with, or 160 centimeters, top one, that one has a smaller slope value than our green one of the same gauge.
Okay, so 30 gauge,
Yeah.
and it's 24.72. 30 gauge, 29. 30 gauge, only 1.2 meters, only about 20. Here we've got shorter wire, and this is suggesting a larger slope. So let's check with this group. Is there a chance those got switched? Is that all we had for length? Here we had length also, right?
Yeah, but then that's.
Well, they're the same gauge.
Yep.
So here the longer one also had a greater slope.
We had one bad data point that we were trying to cause the microphone.
That's a lot.
Well,
of
let's decide as a group. Do we feel that a longer wire should have a greater slope? It would be nice if there was a way to check that,
a giant something in physics or something.
like a giant something of physics or something.
Yeah.
Well, let's keep talking and maybe that giant something of physics will show up.
I feel like all of these.
But I think it's good to say with two of the groups suggesting that.
Maybe put it on one graph.
Like, what do you think the general
Whoops. With longer wire. Okay. Now let's take a look at the units and see if we can't conceptualize what that slope means. We start out with a volt over an amp. Wait, did most of you use joules over coulombs?
Yeah.
Okay, so inside a volt is a joule over coulomb. What was inside an amp?
Coulombs per second.
Coulombs per second. Did everybody try and simplify those?
Yeah. Joule
Very
seconds
good.
and coulombs.
Joule seconds per coulomb squared. Did anybody go inside of a joule?
I mean, I guess you could like, it's like program.
We don't know what's in a coulomb.
But when you.
Well, coulomb is an elementary one. It's not going to have anything inside it.
Yeah.
There's really no point breaking it down.
I would agree. You could keep substituting in, but it doesn't get any easier and it doesn't get to something we recognize. So for us, when it's something we don't recognize, something brand new. All right, so the slope of that potential difference versus current graph that has that set of units is a new quantity, something new for us. Let's see if we can't narrow in on exactly what it is. Let's start with the joule per coulomb. We know that that relates to the energy per charge, or the potential difference, right? And I'm going to add that the number itself is the potential difference required. And what number relates to that?
The rate.
Yeah, so it's the potential difference required for
The rate.
How much? What would be the number? Even though we don't always write it in the denominator.
1.
For a current of 1.0 amp. So conceptually, that's what the slope is. It's the electric potential difference required for a current of 1 amp. It's the energy per charge so that I have a flow rate of 1 coulomb each second. So it really ties back to energy, right? And when you compare the two, and we decide that, hey, a longer wire requires more energy to have the same current, or a thicker wire requires less energy for the same current, it almost seems like there's something about those particular wires that either opposes or doesn't oppose that flow of charge. So you're going to connect the opposition to the flow of charge with it resisting the flow of charge. Is that a nod yes or a? All right, and that's exactly what it is. Some of you are a little bit more familiar with that. We do define it as electrical resistance. And we represent with a capital R. And we can think of it as the opposition to the flow of charge. While we're at it, we've got the symbol R for it. Should be no surprise that this whole mess of units, that's also given its own name. That's an ohm. And to further make it a little bit more interesting, the symbol ohm, or the unit ohm has its own symbol. I know, looks Greek to me too. Greek letter omega. The reason I think they do that, we just take a little sidebar. If I write this, you have no trouble saying, yep, 1.5 volts. Or if I write this, okay, he probably means 3 amperes. If I write this,
It's 150.
it's at 150, and I forgot the units. Is it 15 or is it 15 ohms? So it's given its own special name, own special symbol. All right, so now we know what that slope is. It's defined as electrical resistance. And I think if we take a minute just to summarize those two relationships with the graph. So if those two were the same length, which one would be the thinner wire? Okay, so let's label this thin and thick. Which one would be a long wire?
Thick one.
Okay.
Wow.
What did our data show? Did longer wires have more resistance or did longer wires have less resistance? Longer wires had more. So this would be shorter. That would be longer. kind of to put the idea of resistance in perspective, if I were to take, let's say, a particular current, the short thick wire to give me this current would need that particular electric potential difference, that amount of energy per charge. But the longer and thinner one would require more. So to get a particular current, one's going to require a greater push, so to speak, greater energy per charge. Let's take the analogy of the hallway out here. Like normally during passing time, you've got 4 doors out here, right? 4 doors over there. And we have, what, maybe 1,000 kids passing back and forth. So 1,000 kids could be like the individual charges. Imagine that they're all going one direction just to make it easier. But let's say for whatever reason, somebody locks all 4 of those doors and 3 of the 4 there. So now the wire goes from very, very wide to a lot thinner. And we still have to get those same students through that doorway in the same amount of time because they got to get to a class that can't be late. Would there be a little more jostling? And
Yes.
exactly. We're okay with that? Conceptually, it makes sense? All right, let's finish this real quickly. We can now write the general model that relates the potential difference, the current, and now that we know what the resistance, on our y-axis we had the potential difference, our slope was the resistance, and on the x-axis we had the current. That relationship is known as Ohm's law.
Just named after one.
Yep. And it's probably the fundamental mathematical model of relationship when we deal with electrical circuits and electrical things. It relates 3 of those key players. It applies not only to the, for example, with your school, we measured the current in your school, and we measured the potential difference across your school. So that related to just your particular school. It also relates to an entire circuit. So individual elements as well as bigger circuits. We'll get plenty of practice with that, I guarantee it. What I'd like to do now is to figure out, because we have slightly different values for the same spool, which one of them is correct. So how could we, rather than that experiment, check to see what the actual value of the resistance of your spool is? It's not written on the back.
You have an ohm meter?
There is a meter, and it is called an ohm meter, but I don't have just an ohm meter.
Do you have an ohm meter physics, a giant ohm meter?
Well, it's not a giant ohm meter physics, it's just
Well, it measures, you're one of the ones that is lots of colors and measures stuff other than.
yeah, we have, and I don't know that they even make an individual ohm meter. We have some digital multimeters. So we have a device there right over here. In a second, I'm going to have you grab one. But it would make sense that if we had a voltmeter to measure the potential difference, and we had an ammeter to measure the current, it would make sense that we would have an ohm meter that measures the resistance. So your spools are still over there, according to your numbers. One partner grab a spool, the other partner can grab a meter, and if you've used them before, you can go right ahead and start checking them. If not, I'll show you how to use them to measure the resistance. And then what we'll do is we'll calculate a percent difference as part of your analysis for each one of them.
Does anybody know how to turn this on?
Did you grab your spool? Right, here, set it down. And can you use one? Okay. Yeah, so that's the off. That measures potential difference. That measures potential difference. That measures current. This little guy right here.
Measures all of them?
No, but it's pretty handy. It's called a conductivity meter. It lets us know if we have a complete circuit.
Yeah.
Yep. This one measures the resistance. So we have a bunch of different scales that we could use. This one says it goes up to 200, up to 2,000, up to 200,000, up to 20 million. So ours, according to the values that we had over there, ours are all less than 200. So we set to less than 200, and we just make a connection. I would encourage you, you're gonna have to, somebody might wanna hold it, but you're gonna have to make sure you have a really good connection, otherwise you'll see the numbers flicker a little bit.
21.8.
That's
Ready, ladies?
29.9. Ooh, nice.
It's the same thing, so yours is a little bit different, yours actually has more things that it measures, but
We were at
you also wanna set
29.8.
yours to the.
Is that turn up right now?
Okay.
Yeah,
Ready?
it's under
What's under space? Even. Stay up. So put your spool down.
Wait,
And then
let's turn it.
I'll just hold it, and I would think you probably wanna go,
Turn it
you
what?
can try it on the sides,
See the resistance.
but if you
from, like,
notice,
the
it'll
finger.
flicker a little bit, but go ahead and try it.
Here.
So try
Nope, completely resistant. Put
going
it.
along the top, or else you can
Really
even go
close
see
to each
where
other.
those two spots are. You could go right
Right
there
here, I
also,
got it.
like the two silver spots. And don't be shy, I mean, they're made to dig right
I think
in.
it's because it's grounded, and I'm not sure like that.
Still
You must be getting some plastic
Alright.
there.
To the tip of your pen.
You have 30 gauge?
Yeah.
What did you get for it?
I'm gonna let you hold on to it. so I
Our
can
number
check the
jumped
smother
all
groups.
over, but we got about.
I think it's a plastic.
The reason it might jump all over is, I'll be right over. Right, and these, yeah, these are all different
Yeah, we
levels.
had it set this rather.
Okay, if you connect on the top of those two, that, and don't be shy, somebody hold it over here, don't be shy, just, kind of dig in. Okay, and then you can see it'll stabilize a little bit.
29.5.
All right, thanks for your patience. All right, let's start over here. That's okay. Space, and they can over here also. So, these are just the different things that the meter can measure. So that's a fresh out. That's potential. That's a current. This one is kind of handy. It's called a conductivity meter. Oh, you're way out there, please, Brad. But it lets us know if the circuit is complete.
Do you guys have 26? Martin?
Here's the resistance, and this is the maximum in this particular setting of measure, so up to 2,000, up to 2 million. All of ours were no more than 200, so you just take your leads and get good contact. They're pointy, so don't be afraid to dig in. So Sarah, maybe hold it right there so it doesn't flip over, and then just dig it in a little bit.
It should be greater than 23 or something.
Okay, so record that for that school. How close were you?
We were at 19.
Shoot for within 5%, right? And then switch
Only there, so
So did you say?
No, I'm just saying that,
Oh, yeah.
we were right on our first
our
one.
first one was spot on. This one we had a bad point, so.
I don't think one had that one like that.
So
Well,
this,
it's a pretty drastic point, that's nasty. That one,
I'll go grab my calculator.
cause that was our thicker wire, so it should have been.
Let us have.
Oh, my mistake, that was ours.
Not
38,200 was the longer wire, so it should have been,
It's longer, so.
yeah, it should have had a greater slope.
Well,
Yes.
now when you compare them with the meter, is that what you find when you measure it directly?
Yeah, that one now came out even greater than the other one, which it should have been.
Okay, use both values, you can calculate a percent difference.
Okay.
Like goes out real.
You can be used before this and figure it out.
That's the meter sheet. It just tells you the forward. And so it's like that.
11.
Is that like when we had that circle, they put the top.
I never used to figure it out.
Okay.
Read 14.1.
Did you do both schools?
Yes.
Okay. And then you can use it to calculate percent difference.
Yeah, we got it.
Let's see the
Did everybody get a
other
chance to measure there?
Let's see. Did you get our other value?
Yeah, the other one's right too.
What is it?
You
We have
can
to
put
do
your
it. We have to
meters
do it.
back once you've had a chance, and then we still have to wrap up this idea about the material, right? Because we haven't talked about that yet.
Charge it. Try to charge it. That's what the. You had to wind up.
You may not have had a good.
This was that big huge patch that it had.
Oh yeah. Yeah, yours is like a couple off there.
So 29.5.
Okay. We've got 2 out of the 3 relationships dealt with so far. Right? We saw that a longer wire had a greater resistance. So we could write that as a proportional relationship. Right? We also know there's a relationship between resistance in the gauge or resistance in the cross-sectional area. How would you write that one?
Is it a linear?
Well, if it's linear, that would mean that when I increase the area, I also increase the resistance.
It's an inverse, yes, one.
Inverse. And in the past, we brought 2 relationships into one. So let's do the same thing. This really focuses in on the resistance of the wire. How would we write that as one relationship?
L over A.
L over A. So length in the numerator and area in the denominator. We played this drill before. If I hold one variable constant by taking it out of the picture, I should see the other one. That one's good. Let's take that one out. Oops. And we see that also. Good. There is a way we could turn that into an equation though, right?
Yes.
What graph would we have to create?
R versus L.
Yeah, we would have to plot resistance in ohms over length over area. Would it be linear?
Yeah.
Think about the relationships it's built on.
Yeah, everything else is linear, so.
The slope would be our constant. And if you were to do this particular type of experiment, I mean, the lengths and the areas, those aren't really going to change. What would be the only factor that might possibly change?
Resistance.
Well, the resistance will change with the ratio of length to area. The material. So the slope of this particular graph, and we're not gonna do this experiment, but the slope of this particular graph that's where the material constant comes in. It's represented with the Greek letter rho. So we could write the model, resistance of a wire is equal to rho times the length over the cross-sectional area. And that material constant is called resistivity. So you have resistance, which is the opposition to the flow of charge for a particular material, but then you have a material constant called resistivity. Say that again for me.
The resistivity is basically the number that this material will resist so much.
Yeah, well, it's the material constant for that particular type of wire. And the reason and we may not use this a whole lot, but the reason I wanted you to see it is because in our whiteboard discussion, we brought up, for our pre-lab, we brought up that you thought length, area, and the type of wire, the material, would affect it. And you're exactly right, it does. It does affect it.
Is there like way to find resistivities, like on the periodic table?
For a pure wire, like if we had just used copper wire,
Yeah.
it's a lookup value, yeah.
Okay.
You can look it up. Those spools are actually designed to do that experiment. It's a little bit more involved because you have to have the relationship between the gauge and to quantify what the cross-sectional area is. There's a much more useful relationship that relates to the spools that we're gonna take a look at. Okay? Because, I'll give you a little preview of it. We did one spool, right? What might happen if you put a second spool into the circuit?
Yes.
I mean, because what would it depend on if I were to say, all right, take a second spool, put it as part of your circuit?
Could we try to choose out like tools with the same gauge and everything and see what that is in an alter level?
Yeah. But what would, if I just said, hey, put the spool in your circuit, what would you ask me?
Parallel or series.
Parallel or series? So if we have multiple resistances in series or in parallel, does that affect the resistance of the overall circuit? And if so, how does it relate to the ones that I added? That definitely sounds like an experiment.
We're gonna do that?
We are going to do that.
Cool.
We'll probably start it tomorrow. That's a lot so far, isn't it?
Yeah.
We're not done.
So are we ready to conclusion for this one or continue?
Well, we have one more concept to deal with in terms of this experiment before you can really write your conclusion.
Okay. So we're just continuing.
We're going to continue on right now. First though, when you think about your schematic diagram that you need to draw, right?
Yeah.
What's the schematic symbol for a spool?
Circle?
S.
There isn't one,
Oh.
but there is a schematic symbol for any device that's put into a circuit that's going to alter the amount of current. And that's really what the spool does. It alters the amount of current. So one of those devices that we put into a circuit to control or alter current, that's called a resistor. So what I'd like to do is give you the symbol for a resistor.
They're all narrow.
And again, a resistor is just well, I'll show you some tomorrow. It's just a little circuit element that you can put into a circuit that would control the amount of current you have. The example would be, let's say we were doing bulb boy again, and all I had for you were those big 6-volt lantern batteries. But I knew that the little bulbs I was going to give you, they only operate on a maximum of 3 volts. Well, I could put a resistor in there
To happen.
to take some of that energy so that I wouldn't burn out my bulb. So the symbol for a resistor, this should get added to your toolbox, looks like this. Now you should be able to draw your circuit diagram. Hang on, we're not quite done. If we go back to our original graph, that one right there. We get information from the slope of the graph, in this case it's the resistance. We sometimes get information from the intercept.
I was gonna ask you if the area underneath equals the resistance.
That's where I'm headed. So the area underneath this one joule per coulomb.
Super long.
This is a very rich experiment. Lots of stuff to learn. That's the way you guys would phrase it, isn't it?
No.
Okay. So this area, the question is, what might it represent? All right, Calvin, walk us through the units. Joules per coulomb.
Joules per second. Joules seconds.
Yeah. That's a unit of power. What's the other name for a joule per second? Watt. I resisted the temptation. That's a watt. So this area,
We appreciate that.
I knew you would. That represents the electrical power. In this case, it would actually be the average power. If we were to hold the potential difference constant and in the circuit, the resistors will dissipate a certain amount of electrical power. But for us, we can use that to build a model for power. So there's another relationship. But we just learned Ohm's law.
What is this called? Power law?
That was Ohm's law. If I substitute in
So it's
for the potential difference, I would get
RX squared?
I squared R. There's another one. But wait, it gets better. There's one more. If I rearrange that for current and substitute it in up here, I would end up with delta V squared. So look at that, you have a nice brand new set of electrical power tools. Yeah, this is a lab that has lots of concepts that come out and will require us to practice quite a bit. But now you've got all the pieces together where you can begin working on that conclusion. There are a fair number of new concepts that popped out at you. Resistance, resistivity, electrical power, relationship between length and resistance, cross-sectional area and resistance. Oh, lots and lots. Ohm's law. Would you like to suggest a title for the experiment? Ohm's law. Well done. Let's make sure your boards get erased, and I think we're going to get the bell in just about a minute. Nice work today. That's a lot to go through. Okay. Oh, is that the unit? Yep, let's get your boards erased, and I think we should be good.
We always do the long labs in our beta journal.
That's just.
He plans it out because he wants us to run out of room in our beta journal.
Oh no, that was the chess one.
So that's 580. Care?